Okay, great. Recording has started. Nice. Just going to join in a second device so that I know what's going on your side. That's fine. Okay, great. So I know you can see on the screen redox reactions, but we will be doing electricity today, right? Let me just get there. Pull up your notes. Okay, it's just loading. So but I won't be going through them with you because, I mean, then what would be the point of the lesson if you can just read on your own? So not to say I won't be discussing what's on them, I will, but in a much better way. I'll put a blank slide in there and just start drawing, right? So this is present. Okay, so all this battery nonsense. So we're gonna start with, oops, there we go. See, nice and fancy, right? I'm just gonna talk to you a little bit. So electricity isn't a very large section in your paper. I like combining it and thinking about it as the electrodes because you've got electric circuits, which they test you on 10 to 14 marks. You've got the electrostatic section, again, 10 to 14 marks. And then you have electrodynamics, which can sometimes be for around 8 marks up till 15, 16. And then you obviously have the photoelectric effect, which I don't group with it because that has more to do with waves and light and all of that and photons rather than electricity, right? With electricity, it has to do with the word electro, right? And that's Greek, comes from the word electron, which you know. And this section is about the movement of electrons. Okay, or rather, we study electrons in this last part of your syllabus for the year because you've done everything else, right? You've done mechanics, you've done well, you don't really do much of anything else. All those, work energy power, Newton's forces, um, vertical projectile motion in one dimension. Those are all your mechanics sections and kinematics, and then there's momentum. Now we deal with, and this is the only slightly different part of your syllabus. Well, there was Doppler, very short, and now you've got electricity. So the movement or the studying of electrons and how they move and how they do their thing, right? So okay. Going to go right ahead and you can see the next slide talks about current and we will discuss current. You would remember from last year, current is the movement of charge or the dynamic charge and charges in motion and electric fields and all of that. And we look at potential difference, which you might be more familiar to you as voltage. And I'll tell you the difference between those two terms and how we use them. Resistance, again, you remember all of this from grade 9, in fact. They introduced you, V equals IR, your very, very basic, very simple equations. We'll talk about power, right? That might be a little bit new. I know it's a grade 11 concept, but I'm not sure if you did during grade 11 or not. So power is quite straightforward, and I'll show you that as well. The battery, just nothing major, just showing you the direction of current, which isn't really emphasized. Ohm's law, grade 11 work again. Connection, series and parallel, that's the heart of the section. They want you to understand why these values are different, these quantities are different, right? So circuits, okay, I'm just going to add in a slide here, and I can start drawing and talking and all of that, right? In fact, I'm going to do it just after this one. Oops. Nope. Yeah, so now we're good. I'm just going to go to draw. Okay, very good. So when it came to mechanics, right, the section on mechanics in your the first term, stuff you're used to, the quantities, the physical quantities we deal with what the Newton forces. Oops, what happened there? Draw. Okay, I think, yeah, it's easier than using OneNote. I think this is fine. You don't really need to. I'll draw big, right? Yeah, no, that's great. Still, no, okay, oh, that's okay then. Right, so first half of the year, we talked about forces and Newton's laws and stuff. The quantities, the physical quantities that you understood was a force, what a force is. You talked about displacement, velocity, right? Velocity, all these vectors, and you spoke about mass. Mass was involved, directions. Then when we looked at an acceleration, important, right? Then we looked at um in Doppler, right? When you did the Doppler effect, when you did waves. So you looked at then waves. So in terms of waves, what are those kinds of quantities? We looked at frequency, right? We looked at period. That's not a vector. We looked at period. We looked at um, wavelength, right? Lambda, all of those things. And yeah, so each section has their own physical quantities that we study and understand and apply then, right? Making equations and all, we'll do all of that, right? In this section, when we talk about electricity, right? Electricity and electrons, remember we're studying electrons. So what happens when electrons start to move? Now you learned in electrostatics that that's the study of stationary charge, okay? But now when those charges move between one point to another, right, from point A to point B, okay, maybe through, sorry, I'll put that there, through some conductor. We'll talk about what a conductor is and different types of conductors now. A to B in this sort of conductor, that's a pretty awful kind of conductor. Let's say this is a section of a pipe, right? And you have all this charge, right? Electrons, all these electrons. You'll notice I sort of use the word charge and electrons interchangeably. Charge is um, well, every electron has a charge. Okay, what is electrons? A charge is simply how many electrons do we have, and or how many electrons are missing. Then that's positive charge, isn't it? So, and each electron has a specific charge, a quantity of 1.6 something that's given to you in your data sheet as a constant, the charge constant. One electron has a certain coulombage, right? We measure charge in terms of coulombs, isn't it? And when we have a whole bunch of electrons, then we count how many electrons and we times that by the charge of one electron, and we get the total charge that we have section. Okay. So when electrons start to move, we call this electricity, right? Or the word electrodynamics isn't really um, used the same as electrostatics is, but basically when this charge starts moving, we have something called a current. Okay, when electrons move from one point to another, and it's very nicely illustrated here as lightning, right? Sorry, not really lightning, but more um, yeah, as a movement of charge, lightning, right? Now let's talk about this current. So current, think of a river's currents. So that, there's the force of water going in one direction, the channel of the river. In this case, it's the electrons that are moving, right, in a specific direction. They're moving along a pathway. That pathway is dictated by the conductor. So long as the material has that conductivity, electrons can flow through it. So electrons are actually jumping from one atom. These are all atoms. Now you know the Bohr's that's BHOR, right? BORH. I don't know how to spell his name, but Niels Bohr, basically his atomic model is the one that we use and study, and it has those concentric rings. Now electrons are on the outside, isn't it? So these electrons are jumping from atom to atom to atom in that conductor. And then that movement of electrons, which is then the movement of charge, because charge is but a bunch of electrons, because they each have a specific charge. And that quantity is what we call as current. And the symbol for it in physics is I. And we'll talk about its relationship with the other quantities in a minute, right? So movement of charge, that's what this is all about. It's about how charge moves. So in a parallel circuit, right, a parallel circuit, um, and simple circuit is what we study, right? So you have a power source, and then just draw like a freehand thing here. Okay, so these are now branched. It's not very nice actually. 2, 3, okay. And then as opposed to this circuit, let's put the thing there. Sorry, it's not looking very much the same. But yeah, that's a circuit. Then let's say there's some resistor there, resistor there. Something that uses the charge basically. Don't get too caught up on that right now. And this charge will flow. We have that nice picture of the battery. Let me just show you. Yeah. So charge flows from positive to the negative side, isn't it? That's the direction of the current. So let's go back to our nice little drawing. Well, not very nice, but our drawing nonetheless. Okay. So this is the positive. That's the negative. So charge will move in this direction, right? Different color, right? So a little bit. These electrons are moving in this direction, right? Now, when it comes here, it gets split up, right? It gets split up in 3 different directions. And so the charge on each of these resistors, thing that uses the charge, will be less, well, in one of them will be less than the charge coming in before it starts splitting up. So the same charge has to travel through this conductor and then has to split up, right? Because of the parallel connection, right? So understand that. Then in simple series, okay, the charge just flows, right? It just flows straight through, and we'll look at that in a minute, as well as just giving you a nice overview, and then we'll discuss it in detail and examples and all that. You know how this works, right? So that was current. Current is moving charge. We spoke about I. Now let's look at potential difference. It's going to sound a bit abstract to you, right? But don't worry. You know that what you've been using voltage all these years, right? Think about voltage. Okay, it's that quantity. It's the same thing, but we now use the more correct scientific term, which is potential difference between 2 points. So let's say there's point A here again and point B here. Okay, in the conductor, so it's like a loop. So let's just do a nice thin conductor, right? That's a wire. And potential difference, the word potential is there's an imminence, so it's not quite there. It's not an actual difference. It's a potential difference. So what would be the difference in charge in a hypothetical situation? And difference is what? This point subtracted from this point, isn't it? But difference of what? It's difference of charge, a difference of energy, right? So the potential difference from this point to this point is the voltage across those 2 points. Okay, it's it's sort of a one thing. Think of electronegativity, right? When you discuss this in chemistry, and you talk about the electronegativity is what? The affinity of an electron, of an atom to attract electrons to it. It's that attractive quantity, right, that brings charge together. How much will charge move from this point to this point? How much charge will go, with what force will the charge push through, right? Now, it also has a slightly different name, and we call this EMF. Well, you don't say EMF anymore, we say EMF. Okay, it used to be called EMF when it first was introduced as a concept, and that used to stand for electromotor force. And it's basically the force that charge would flow through a conductor, right? And that makes sense. But then, after some investigation and criticism, it was decided that this quantity is not really a force, because then it would have to be measured in newtons, isn't it? All forces are measured or must be able to be measured in newtons. And there was no way that the scientists could get this quantity to be measured in newtons. But it is a quantity. It does exist. We know that it exists. Okay, it's how much is this charge being pushed through this conductor. And when you think of a pushing factor, we think about force, isn't it? Because a force is but a push or a pull. But in this case, it's not a force that's pulling this charge along. It's the potential difference. And well, we gave it the name potential difference, but you could also call it voltage, but that's not quite correct, and I'll tell you why now. So instead, it was just left as EMF because all the books had it in there. But now we pronounce this as EMF, right? And it's going to sound a little funny to you because I know your teachers in school are not going to say EMF, they're going to say EMF. That's a much older version that we don't really use anymore. It's called EMF, right? And it sounds like a little mythological creature, doesn't it? Like an elf or a hobbit or something. But no, it's an EMF. And the EMF is basically terminal potential difference, meaning the potential difference across the cell. So the maximum potential difference that can be delivered to a circuit is terminal potential difference, is EMF. Okay, not EMF, that's electromotive force, and that doesn't exist anymore. It's not a thing. But it's easy to understand it as what it was first thought of as electromotive force. It's the pushing force that drives charge through a conductor. Okay, it propels the charge along, but it's not a force. Okay, remember that it stands for M. It's just M. It doesn't stand for anything anymore. It's M. Okay, so, and there was a nice picture, I think I'll show it to you, where it's like I'll try and draw it for you. So there's a thing there, like a little dip there, and the rest continues and then continues out. So this is the conductor, and then there's this fellow here, okay, who is putting like a wire through here, tightening it. Very mean. And then there's this fellow here, which is a different color. It's trying to crawl through the space, and then there's this fellow here, right? That's sort of like pushing him along, pushing, right? Pushing. So he's trying to crawl through this space. He's tightening the space, and this fellow's pushing him through. So this is a nice illustration of resistance. Okay, resistance, charge, or current, and voltage. Okay, isn't it? Voltage pushes the current through. The current is what's moving through the conductor, and then resistance is trying to stop the movement of current through it. So that's a nice illustration to help you understand the quantities and how they interact with each other and relationships, because that's the branch of your syllabus, isn't it? Understanding relationships between physical quantities and working with that mathematically. Now, we spoke about what voltage is. Let's look at our nice pictures that I put for you. Yep, there we go. This is your formal definition that you'll use. The amount of work done or energy transferred from 1 coulomb of charge to 1 coulomb of charge as it moves between 2 points. You will learn that, you'll study that, and you'll regurgitate that in your exam, right? Now, electrical potential difference referred to as voltage. I'll tell you why. Again, now don't worry about this little block thing here, negative W over Q. Use it in terms that you're familiar with. I know this W, just call that work, and U, it's potential energy, but don't worry, and then this charge. We'll talk about that just now. Then it can be measured in joules per coulomb because by the definition, amount of work done, the energy transferred from 1 coulomb of charge to 1 coulomb of charge as it moves between 2 points, okay? So it's, yeah, spontaneous movement of charge from a high electrical potential energy to a point of lower electrical potential energy. Then that's what pushes it along, because there's a lot of charge. Let's go back here. There's a lot of charge in one area, so lots of charge, lots of charge, lots of charge, okay, lots of charge, and then no charge, it's deficient. So charge will move here because of a gradient, because of the potential difference, the difference in energy, because this is more electrical energy, sorry, here, and he has less electrical energy. So there's potential electrical energy, which you don't study, but that's how we get the term potential difference, because it's when this moves there, it's this part is going to be deficient in electrons, and this part is going to have all the electrons. And so there's a difference in the amount of charge that each portion carries, and in order to move that charge along, there needs something to be pushing it, and it's that deficiency, right? You'll understand this more if you study, think about osmosis, something of high concentration or diffusion from a high concentration to a low concentration. That's the natural order of things. That's a bit abstract, so don't focus too much on it. They won't be asked about it like that, but it helps for understanding it. Just know that it pushes charge along. Okay, potential difference is that quantity that pushes charge along, and it's measured in V's, in volts. Okay, volts. So if you want to know, if you want to quantify potential difference, you'll ask for a voltage. What is the voltage of that specific component or something like that, isn't it? So voltage is it's measurement. Okay, like current is measured in amps, isn't it? And if you want to know, ask for a quantity, you'll say, what is the amperage? Okay, amperage. Okay, so just like that, we can ask what is the voltage, and that refers to how much potential difference is across 2 points. It'll always be between 2 points. And what measures potential difference? A voltmeter, right? A voltmeter measures potential difference. What measures current would be an ammeter. Okay, you know that measures amps. A there. Okay, and I'll talk to you more about that later on when we get to those exam questions on it. Also, ampere, if they ask you what is current measured in, and they will ask you that at some point for 1 or 2 marks, do write the full word, right? Ampere, the older versions have that little flick at the top, it's an accent. Do not just write amps because the memos are very strict, you won't get marks for that. Okay, so now let's talk about resistance, okay? The third electrical quantity that's important to you right now. We spoke about voltage. Let's look at resistance. Oops. Now what is resistance? So again, it all comes back down to this movement of electrons through a conductor, the movement of charge. So these are electrons moving along, okay? And this is the conductor. Obviously, it's moving through the atoms and all of that. Now, if you push a block, okay, I'm going to take you back to things that you know. You're very familiar with mechanics, okay? If you push a block, this is you, it's nice here, and you're pushing this block that direction, and it's rubbing against this rough wooden floor, what's going to happen? You're going to have a frictional force opposing motion, isn't it? Fr or Fk, whatever you want to call it, friction. Okay, so just like that, these electrons in the conductor experience friction. Okay, now we don't really use forces in conductors and electricity. That's not really in your syllabus. So but just know that it's there, and that friction causes the charge to be it makes it difficult for it to move from one point to the next, isn't it? Because it opposes the charge's motion, isn't it? So resistance is the opposition in the movement of a charge. So opposition movement of charge, and it's all in the notes here with diagrams and everything. So this charge has trouble moving through. So obviously different conductors will have different resistance, isn't it? It'll oppose charge slightly differently depending on all sorts of things. What things does it depend on? Yes, they can ask you that. So factors that affect resistance would be what? For example, thickness of the conductor, isn't it? So how so? This will obviously have less resistance as opposed to this. Okay, so a thicker charging cable for your phone will charge much faster than a thinner charging cable because there's more space for the same amount of electrons to flow through, which means they will flow through faster, right? It's just simple. So thickness of conductor, then again the length of the conductor, of course, because the longer this charge uh, is flowing through the thing, the more opposition it's going to encounter, right? The more resistance it's going to experience. So longer cables will offer more resistance than shorter cables. Okay, think about it like the thing about your charger. So if your charger was shorter, it would charge faster than if it was longer. And that's just because electrons have to move through more wire, they have to brush up against more atoms, they experience more friction. So it's the length of the conductor, the thickness, and then there's temperature. Okay, how does temperature affect things? Well, you know, when it's warm, okay, when it's warm, the electrons can flow through quicker. That has to do with, of course, the kinetic molecular theory and all of that. You understand that. So the warmer it is, the higher the temperature, the less resistance is experienced, and so forth. And then there's another factor which is of course the type of conductor, because some metals simply allow electrons to flow through them much more easily than other metals. Okay, you won't be asked why or which materials, but we know the best conductors are what, gold and platinum, and then more affordably copper. And like tin isn't a very good conductor. It can be, but it's not really. Aluminium is not a very good conductor of electrons, or compared to the more precious metals. Zinc is not a bad conductor, and things like that. You won't be asked any of that anymore. You were in grade 9, I think, but that stops there. So that's basically what resistance is. If you look at the slide, you can see there's a nice diagram and everything that I gave you. And yeah, it's all there, so don't worry. And the formal definitions are in bold that you can learn for the exams and all of that. And then electrical power and all of that. So I'll show you how we do that now. Yeah, there's a delta. You'll notice there's a delta in some of my slides here. That just potential difference, because it is a change, right? You know, delta in physics means change. So don't worry about that, because your quantity, you'll just use V. You don't have to put the delta. It's just more accurate, but don't worry. You'll still get marks for not, even if you don't, so don't worry about that. I know it seems like a bit like it's dragging, a bit tedious right now, but once we get to the examples and you'll start to appreciate how easy the section is. You can really score a lot of marks. Even electrodynamics, you just memorize a few things. Electrostatics is fun, and we will go through that. The equations are nice, if you think about them in terms of the gravitational forces, right? It's this very similar thing, m1, m2 over r squared, q1, q2 over r squared, right? Very similar, and that's quite interesting. So electrical power. Okay, so now let's look at that relationship that we saw with those three quantities that we just studied. Well, the equation is V equals I R. Okay, so when you increase current, the higher current you have, the higher velocity, sorry, higher voltage, my bad, greater potential difference. So that V is, but this is a capital V. So because they're directly proportional. Okay, the more resistance that you have, all right, think about it like this: the more that current is resisted, okay, the more potential difference you require to push that charge along in the conductor. Okay, the less resistance you have, the less voltage you need to push the current along in that conductor, and so forth. Then you can manipulate this, and you can say, you know, I is equal to V over R. Okay, so now current is inversely proportional to resistance. Okay, obviously the more resistance you have, the less current will flow through, because the charge will be opposed greatly. So it's just simple relationships and conclusions that you can make from that, right? Same thing you can say with the resistance. Well, yeah, is the same thing, V over I. So you don't need to learn all of these. You just V equals IR, and then you can extrapolate whatever else you need. And now there's another thing. How do you measure power in a circuit? Power, I'll give you the equation, is um, IV, right? Voltage times the current. It's your potential difference times the current flowing through, and that's the power that's delivered, and that's in that specific length of conductor or entire circuit, depending on what you're measuring. And what you're measuring across from is always between 2 points or the entire circuit. Okay, so because from one end of the conductor to this other point in the conductor, what is going on within this one length, and that's about it. You don't really work with plates or anything like that anymore. That was taken out of your syllabus a while ago. You know, you get these charged plates, and then you like how charge moves between them. You don't really do that anymore, though that is very interesting. But so power is IV or VI, however you like to say. It's the same thing really. But now let's derive some stuff. So I equals V over R, isn't it? So power is equal to V over R times V. That looks like V squared over R, isn't it? And it is. That's the same thing. That's fine. And then power, we said, is IV. Right now V is IR. Okay, so let's do some derivation. I, then this V we said was IR, right? And we can just say equals I squared R. Quite simple, isn't it? And then let's see, there are a few other derivations of these. Uh, Yeah, so V squared R, I squared R, those are your three equations that you can use. I'm just going to go back to current very quickly and give you I didn't finish giving you the formal definition, which is rate of change of charge, okay? So it's a rate of charge flowing through a conductor. And the rate of something in physics, as we said, power is the rate of work done, right? You just divide by time. So Q over change in a certain amount of time. So how much electrons are flowing, the quantity of charge that's flowing divided by how long it took to flow between those 2 points is going to give you current. So I equals Q over change in time. Okay. And you can work with that in other situations as well, and you'll see it can be very helpful, especially with the photoelectric effect section. And I'll show you that later on when we get to it. And I'm saying a lot of words now, I'm talking a lot, and yeah, but you need to understand the basics first before we do anything more complicated, or you will get confused, right? And then they can ask you to work out. So this is all very straightforward. Okay, kilowatt hours, and there's one more equation which I will show you. So this just tells you exactly how to work it out. Very rare. I will show you an example, so I won't really go through this one. That's for you to go through. Battery, not important. Ohm's law, right? So an ohmic device has a perfect slope of V equals IR, right? Ohm's law is what I just explained to you, that whole relationship where uh, current is directly proportional to potential difference as long as temperature is constant. And then the slope is going to be resistance, okay? Now, a non-ohmic device, which doesn't follow Ohm's law, which does happen, like when temperature is not constant, that's not an ohmic condition, then you'll find the slope. So just learn what these look like, and then you'll see there's nothing more they can do with that there. They can't really ask you to work out gradients and stuff. That's more in your practicals and whatnot. Right, so connection of components, as you can see. So you have a circuit that's in series where one component is connected after the other. There's no separation, there's no splitting. Current does not split. Okay, and you see the explanation I put there. It looks like links in a chain, right? So output of one is connected to the input of the other. Let me just draw it off. So this is the output of one connected to the input of the other. So the output of one resistor is connected to the input of the other resistor, and so forth. Okay, so like links in a chain. And then we have current is equal at any point in a series circuit. Current is the same. I showed you why. It doesn't need to split anyways. It just keeps continuing along nicely. Now the voltages add up because your voltages are split. And this works better when I show you examples, okay? And then resistance also adds up. And adding resistance, that also gets a bit interesting. We'll need a lot of practice there, okay? In parallel circuits, it's split up. Your conductor splits. Okay, you have split separations in your conductor, which means your current has to divide. Okay, if your current divides, then to work out total current, well, you need to then add them up. This is supposed to be IT, VT, VT, IT, there like that, right? Or EQ, you can use EQ or you can use T. This EQ stands for equivalence, basically means the equivalence of everything in there. So you can use T or EQ, it's the same thing, right? And then, yeah, now with current, it's 1 over R. Sorry, resistance is 1 over R, it's inverses. And yeah, so again, nothing major. So all the inputs are connected together. You can see this is the input, that's the input, that's the input, all connected at that one point A, and all the outputs are then connected at that one point B. So this is a parallel circuit. These are more formal definitions, rather you can use them. But the explanation is simple. Current splits, conductor splits, current does not split. Okay, it's not that confusing, so don't spend too much time, right? So in a series circuit, currents stay the same, voltage adds up and resistance adds up. In a parallel circuit, voltage stays the same, current adds up, and your resistance is upside down, right? Sum of the inverses, basically. And then that's just for you to read. F is, yeah, just for you to read. Lost volts and stuff, I'll show you now, don't worry about it. And these are all your equations that you can use. So work is equal to I squared R change in time. Why is that true? Because power equals IV, and this is V. Work is changing. Work is power times time, right? You know that work is power times time because power, right, equals work the rate of work done. The rate of something is it's the quantity divided by time. So the rate of work is power, which means that W is power times change in time, and power is I squared R. Power is IV, so you can also say IV change in time. Power is, oh yeah, there it is, yeah. All sorts of things. So these are the main equations that you can use. And everything nice and summarized. Okay, so don't worry too much. So you can go through this example on your own. Stop around here first. So now the first example. Nice. When we look at, just when I get this closed. Oh, nice. I can zoom in. I don't need to zoom in, but I can do that and get a full screen. Now the method that we use is quite interesting. I'll show you that when we start a full circuit, but let's add the we're adding, oh, there we go, good. You can use a different color actually, slightly thicker. Oops. That's too big. Okay, that's better. So basically, we're just going to find the sum of the resistance here. Simple. So this one, it's just 6 ohms. 6 ohms. There's nothing complicated here. But now here, we have a split. Okay, and that split means don't ever have my calculator on me. I'm doing these things. Okay. That split branch means that this branch is in parallel, right? And how do we add resistance in a parallel circuit? So R total, or 1 over R total, is going to equal to 1 over the 7.2 ohms plus 1 over the 14.4 ohms, right? And if you're going to work this out to show it algebraically, you'll say then RT, or rather RT. I like using to the negative 1 instead of 1 over. I think it just looks easier to write. So it's going to be 1 over 7.2 plus 1 over 14.2 all to the minus 1, and that's RT. So you can put this in your calculator as it looks, but then what if you have a third branch or a fourth branch? It gets quite complicated. So you need to also be smart about how you use your calculator, right? So type in the figure. We're going to do this together. Type in 7.2 ohms. We don't have to put in the ohms, 7.2. And then there's a key, right? There should be a key which looks kind of like this, a block with a -1 there, right? It's like an inverse kind of thing. If you have that FX991ZA plus, the silver thing, then it's somewhere at the top on the right. So you press that key and it inverts your number, right? So then you add the second quantity. So you remember you typed in 7.2, you press this key, you now see a -1 there. Then add to that the second figure, which is 14.4. And then do the same thing, press this key again. What that does is it gives you the inverse of that. Then you obviously put equals 2 to get an answer for the sum of the inverses. But that's not your answer, right? What you just found was 1 over RT, whatever is written there. And that should be, I think, 5 over 24, isn't it? Now, the easier thing to do is don't do anything after that. Just press this key again, this one here, the inverse key. Then equals 2, and you have the correct answer. Just to get it in the correct decimals. Let me take this out, sorry. So that inverse key is very useful, and you just need to train yourself with using it. It's much quicker, you save a lot of time. You want to finish the section in like 10-15 minutes in the exam, right? It's very simple. And so the sum of these branches, okay, or the total resistance of this branch is 4.8 ohms. Okay, so now it's in series, or rather doing the equivalent circuit thing, we can just do that and 6 4.8. It's the same as this. It has the same electrical behavior as that, which means that the sum of this branch plus 6 is going to give you a total resistance. Now this should be parallel. Specify that, right? Of 6 plus 4.8, 10.8 ohms. Okay, so let's look at the next example now. So we have now two parallel branches, and the method that we use is you ring your parallel branches. Okay, put them in little rings. Then you find the totals, and then you just add them to whatever's in series. So got a ring there, got a ring there. So again, it's going to be 10 inverse plus 10 again. So 10 inverse plus 10 inverse equals something. Invert that, and you get 5 ohms. Okay, should be doing this with me. If it's, you can pause also and get the answer and check if it's correct, because these are recorded. Now for this branch, it's going to be 2 inverse plus 3 inverse. Okay, get an answer, then you invert that final answer, and you get 1.2, right? So 1.2 ohms. So then RT here, the total resistance, so you can say RQ, whatever you prefer, is going to be the sum of everything. So 5 plus 6 plus 1.2. Okay, that's what 11, 12.2 ohms. All right, now here, what do we do here? Well, here we can just call this 12. I'll draw. So we can just ignore this, and there's one resistor here of 12 ohms, and now we have a ring and that 4 ohms. Okay, so the total resistance of this branch is going to be 12 inverse. The methods that are very, very important in physics: 12 inverse plus 8 inverse plus 9.6 inverse, right? 9.6. And then you invert that last bit there, that answer, and you get 3.2. I should be getting 3.2 ohms. And this is 4 ohms, so you add them together. Total resistance is 3.2 ohms plus 4 ohms equals 7.2 ohms, right? Now what's going on here? The examiner is trying to trick you, right? Your physics examiners are very suspicious like this, right? They like complicating things for no reason. You're going to look at this and get scared, but don't get scared. Why? Because you can look at it like this. Okay, that's again the thing I said about drawing equivalent resistors, equivalent circuits. You can redraw this and it'll look like this. So it's a little off, but that's there. And this is going to be 6 ohms. It's going to be 2.4 ohms. It's going to be 6.8 ohms, and there's going to be 10 ohms. So, which then can also be simplified into simply what are you looking? So 6 plus 2.4, this is 8.4 ohms, and this is 16.8 ohms. Right, and then you just ring that and you do the calculation and you're done. So what is that going to be? In fact, 8.4 inverse plus 16.8 inverse. Okay, get an answer, invert that final answer to get 5.6. And that's the total resistance, right? RT equals 5.6 ohms. All in your calculator, right? Easy. Now, what's going on? If you look at this, look at how current is flowing through here. Charge is going to move, and then it's going to split up. But then it doesn't split here, it just keeps going. It's just a connection in the circuit, so it just keeps going. And then it rejoins at this point. So there's only this branch, this is one branch, and this is the other branch. So it's the same as just making it like that. The examiner just wanted you to be a little bit confused and question as to how you're doing this, but don't overthink, don't let them get to you. Just remember the basics, right? Which is look at how the branching works, and then you'll know what's in parallel and what's in series, okay? Once you have that, then you're done. So even this looks a bit complicated, but it's not. Everything is in parallel here, right? This whole thing is a branch. Oops. If you just look at how the current splits, okay? So let's look at how, oh, sorry. Look at how the current splits. So we're going to go here. We're going our first bit is going to be there, then it keeps going, but then it splits again, right? And then it splits here. Okay, then this keeps going, and then it rejoins at this point, and this rejoins that there, and this joins here. So this is one branch, right? And then this is a bigger branch with that equivalent resistance. Make sense? Right, so you find the small branch first, because that's where the split happens, and you find the equivalent resistance of the single branch where it splits with this branch in parallel, right? So let's simplify a circuit like that. Okay, and then just to show you, this is going to be the 20 ohms, and this is going to be the equivalent of that, the 10 and the 10 here. Okay, so the RQ for this branch, EQ for this branch is going to be here. So let's find that first. It's going to be 10 inverse plus 10 inverse inverted, which is 5, right? 5 ohms. So this is 5 ohms. This branch here, this one circle is 5 ohms. So it's 20 and 5. That's a branch ring that. And 20 inverse plus 5 inverse, all inverted at the end, is 4, right? So 4 ohms. And that's the total resistance here, 4 ohms, right? So that's, again, just look at how the branching happens. Now they've given us here that the total resistance is 7 ohms, and they're asking us to calculate that. So this is quite easy. Again, do your rings. Oops. It's one ring. That's another ring here. So it's R plus whatever this branch is, that's R, the parallel branch, is equal to this thing here, right? Or R is equal to RT, so the 7. So 7 equals R plus R parallel. How do we find R parallel? 12 inverse plus 6 inverse, all inverted. So 12 inverse plus 6 inverse equals all inverted, and that gives us 4. Okay, 4 ohms. So if R parallel is 4 ohms, then this R has to be 7, sorry, 3, if everything is 7. So this is equal to 3 ohms, right? This has to be 3 ohms because 3 plus 4 is 7. See how easy that is? Now, same situation here, a little bit more interesting, rather. This RT is 4 ohms. Okay, so we can ring this. And let's write it down. So 12 plus R minus 1, 12 minus 1 plus R minus 1 equals RT minus 1. Okay, and we're solving for this R here. So RT is 4. Let's do that. So 12 minus 1 plus R minus 1 equals 4 minus 1. Isn't it? So R minus 1 is going to be inverse of 4 minus inverse of 12. Now you know that the inverse of 12 is much smaller than the inverse of 4 because inverse of 12 is 1 divided by 12 parts, and this is just 1 divided by 4 parts, so it's much bigger. So this is not, you don't get negative resistance, that doesn't exist, right? R is greater than 0, or greater than equal to 0 for all R is an element of real number. That's getting too mathy, but basically resistance has to be positive, right? You can't get negative resistance. That doesn't exist. Like how you can't get negative time. So you can just do this in your calculator. You can say 1 over a quarter minus 1 over 12. That's your answer, right? It's not too complicated. You'll see in finance that there's more interesting equations to do. So just put that whole thing in there, and you get 1 divided by inverse of 4. You should be working ahead of me, minus 12, inverse of that, and I'm getting an answer of 6, right? So R has to be 6. And if you check that, if you say 12 inverse plus 6 inverse, you will get 4 inverse. And actually, we did do that here. See, 12 plus 6, R parallel is 4, so it is correct. And now let's do that again. So we basically want to be left with a parallel branch. So you start off with your full equation, which is, oops, yeah. So RT equals 4.4 ohms plus R of the parallel branch. So R of the parallel branch is going to equal to total resistance is 8 ohms minus 4.4 is going to be 3.6 ohms. Okay, so this ring, right, it has a total resistance, a parallel resistance of 3.6 ohms. So we just do what we did earlier. So we say 3.6, 1 over 3.6 equals 1 over 9 plus 1 over R. Okay, or rather small r. So 1 over r has to equal to 1 over 9 minus, sorry, 1 over 3.6 minus 1 over 9. So you're good, right? So r is going to equal to 1 over that whole thing, 1 over 3.6 minus 1 over 9. And you do that on the calculator. Your calculator can do a lot of things. Okay, trust it. You'll be fine. And the answer is 6 again. Okay, so pretty cool. That r has to be 6. So 9, 1 over 6 plus 1 over 9, 1 over that whole thing, plus this gives you 8. That's basically how to separate resistance at parallel. Oh, so this is an interesting question. Show how 3 6-ohm resistors can be arranged to produce 1, 2, 3, 4, right? So try different things, okay, obviously. How would you produce an 18 ohmage total resistance? If you have 3 identical 6-ohm resistors, obviously, you're going to do this. You're going to say, right, sorry, but oh, that's the other thing. So you notice I'm using the zigzaggy thing for resistors when your exam and stuff. They'll use that little block square thing, which is kind of silly. It's the same thing. Don't get too bogged down in that. It means the exact same thing. In fact, the zigzag one is more correct, more accepted in the scientific community. So, like even if you do this in university level, you will use the zigzags, not the squares. So I don't know why the exam board likes those, but don't, obviously, if you see it in the exams, don't say, oh no, I don't know what this is. It means the same thing. Treat it the same. It's not that big a deal, right? So obviously, if we have it all in series, we're going to get 6 ohms plus 6 ohms plus 6 ohms. RT equals 18. Nice, isn't it? Now let's try something else for number 2. What do we do for number 2? Let's do a 1. It's not intuition. You can actually try all the different variations, add them up and see what you get, and then present that as your answer, right? With me, it's a bit more intuition because I did this a bit longer than you, but that's all, right? So this would actually be in a multiple choice question. They can ask you and give you the options. I just put all the possible things here, but they can say this will be the question and then give you options A, B, C, D, right? And stuff like that. They can be quite creative with these things. So know how to do it back to front. Cool. Now let's find this. Yeah, that's 6 ohms. This is 6 ohms. And this is 6 ohms. So it's going to be the 6 plus this parallel branch. Let's calculate that quickly. And it's going to be, well, I actually know the answer, but do it anyway. So 6 inverse plus another 6 inverse. Get an answer. The inverse of all of that will give you 3. So 3 plus 6, yeah, this is 9. So RT here is in fact 9. That's correct. How would you get 4? I don't know. What did we not try? We didn't try putting all 3 in parallel. They're all 6 ohms. So it's going to be 6 inverse plus 6 inverse plus 6 inverse. Inverse of all of that is 2 ohms, right? So this is 2 ohms. Well, RT. So we've done number 4. How would you get number 3? Only 4 ohms. So they are it is possible that they wouldn't have asked it. So how can you arrange 3 6 ohm resistors so that you get a total of 4 ohms, right? So just try and figure that one out, and we'll give you the answer in when we're done with the solution set to these, right? So interesting questions. When two identical resistors, when you know how to deal with them, two identical resistors are connected in series. Okay, let's draw that. Let's draw and see what's going on. So it says two identical resistors. So draw some resistance R, let's call them R, connected in series as such. So the total resistance is 20, which means that doesn't take a genius to know that R plus R equals 20, 2R equals 20, R must equal 10, right? You don't need to be very intelligent to know that. So that's fine. That's just a 10 and 10 ohms each. So they have 10 ohms each. So what's the total resistance connected in parallel? That's easy. Just draw it again. Right, I recommend highly getting a schematic of what's going on before you start doing a solution. It's very helpful. So 10 ohms and 10 ohms in parallel, you know our method. It's going to be 10 inverse plus 10 inverse, and the inverse of all of that, which is just 5. So 5 ohms. And that answers the question. So done. Two identical resistors connected in parallel, the total resistance is 12 ohms. What would be the term if they connect in series? So this is the same thing as earlier, just backwards, right? So now they're in parallel. What is it going to be in series? We need to set up an equation first. Before we do that, we need a schematic. Okay, so let's draw what's going on. Two identical resistors in parallel. Let's draw that. This is R and R, and RT equals 12. Set up an equation. So 12 is going to equal to 1 over R plus 1 over R, just some maths here. 12 equals 1 over R plus 1 over R is what? R plus R over R squared, isn't it? Yeah, that's it, which is 2R over R squared, and don't cancel here. Okay, don't cancel. Just keep going. So we say 12 equals R, 2R over R squared. Okay, what do you do? Move the R squared to the other side. So 12R squared minus 2R equals 0. Let's simplify. 6R squared minus R equals 0. And then now you factorize. So when you get a division of unknowns, you are not allowed to cancel because you're not allowed to divide two unknowns. In maths, that's not allowed because it's called losing roots. Okay, losing roots. Okay, so we don't do that. So you factorize, don't cancel. Remember that. Even when you're doing maths, calculus, especially in your section, it's factorize, don't cancel. Okay, that's the golden rule. Now let's continue with this. It's going to be, well, R is a common factor into 6R minus 1 equals 0. R equals 0. All 6R minus 1 is 0, which is just going to be R equals 1 over 6. Okay. And what is 1 over 6? Well, you need to find an answer to that one. Well, a decimal answer. And 0 0.1, sorry, 0 point, what was that? 0.17, right? Make sense? No, this is wrong, right? We missed out this here. It's not wrong, it's just not entirely right. Okay, so it's nothing major. We just didn't put the 1 over here because it's 1 over RT that's equal to that. So we just put 1 over. Doesn't change much, except that our final answer is just going to be 1 over this. Therefore, R equals 6, okay, because it's the inverse. So 1 over R equals 1 over 6, R equals 6, right? So 6 ohms. That's good. And now determine the value of each resistor if total resistance is 9 ohms. That's not very hard. It's just going to be R plus 2R plus 3R equals 9. 6R equals 9. R equals 9 over 6 equals 2 over 3, which is 0.67. Yeah, ohms. Right? Always don't forget your units. That's very important. Now, what is the value of the parallel section if RT is 12 ohms? So they want this. Well, they don't want much from you in this question. Let's just look at what they're asking you. They want to know this parallel section, right? If total resistance is 12, that's quite easy because it's just R plus R parallel, that's equal to RT, isn't it? So R plus the parallel section equals 12 ohms, okay? And we can work this out. Let's do some more maths. I know you all don't like doing this, but physics does have quite a bit of maths in it. Okay, let's do this. So it's R plus R over R squared, as you remember that we did, you know what that's going to be from before. Don't worry too much about that. Well, I'm going to say now 2R over R squared. It's a little bit more work. Well, it should be the same R, sorry. Not two different R's. 12. Okay. Well, now you're just going to get, if you multiply everything by R squared, you get a cubic. So, because that would be the only way out of this. But let's say we could cancel. Let's simplify this actually. R equals 2R. It still doesn't work even if you do cancel, but let's for the sake of it say you are canceling and you choose to cancel. No, you're not supposed to cancel. Don't ever cancel. Never mind. That's the golden rule, remember? So the only way to solve this equation would be to multiply everything by R squared. And if you know your maths, so yeah, this is going to be R cubed plus 2R equals 12R squared. Let's bring that in standard form, please. 3 cubed minus 12R squared plus 2R equals 0. Now you can go ahead and remove R as a common factor from all of this. You get R squared minus 12R plus 2 equals 0. Either R equals 0 or R squared minus 12R plus 2 equals 0. Let's see if we can factorize this, or if we need a calculator. So 2, no, you do need a calculator for this, I think. 5. You can use even the quadratic formula that is allowed, you know, the b squared minus 4ac, all that whole thing. So it's minus 12 plus 2. And I get a very funny answer of 11.83 after doing that. R equals 11.83 or R equals 0.17, right? 0.17. You'll need to try both and test it, and then just find the spot 2R over R squared, because that's the value of the parallel branch, isn't it? Yeah, and that's about it. So again, it's just about understanding how to work the branches. Now again, you're probably tired now, but gotta keep on going. Okay, your exam is long, 3 hours. The effective resistance, or the equivalence, it's all the same thing. Equivalent resistance, total resistance, all of that, right, is 10 ohms. What is the value of this R here? So I know that this branch is going to be 1 ohm, because this is 9 ohms. So 9 minus, well, that minus 9 is going to leave me with 1 ohm for this branch. And that simplifies things a bit, doesn't it? So I know that 1 over 1 has to equal to 1 over R plus 1 over 2. Okay, and I know that 1 over R is going to equal to 1 from 1 over 1 minus a half. 1 over r equals 0.5 or half, so r has to equal 2, right? Makes sense, and the answer is C. Study the diagram below when an additional resistor was connected in parallel across the 12 ohm resistor. So let's redraw this. Okay, let's redraw. Eight ohms here, 12 ohms here, an additional 12 ohm resistor here. The total resistance becomes 12. Determine the value of the additional. Oh, we don't know what the additional is. My bad. There's some R. Okay, and the total resistance is 12. So this whole thing, which means R parallel plus 8 equals 12. Okay, so the value of R parallel has to be 12 minus 8 is 4 ohms. Okay, if we know that, we can say 1 over 4 equals 1 over 12 plus 1 over R. You know how this works. 1 over R equals 1 over 4 minus 1 over 12. R is equal to 1 over 4 minus 1 over 12 all to the minus 1, or you can say 1 over the whole thing. Same thing, let's get an answer, right? So I'm going to say 1 over 4 inverse plus 12 inverse. And the answer is 3, right? So R is equal to 3. So the value of the additional resistor is 3 ohms, right? Next question, we're almost there, getting there. I think. What is the value? We'll do circuits just now, don't worry. The effective parallel resistance is equal to the resistor in series. Okay. What is the value of R? The effective parallel resistance. So you also need to understand the terminology. That's what this is testing you. Effective parallel resistance. So this whole parallel branch here is equal to the resistance series. So it's 1 ohm. Okay. What is the value of R? It's going to be 2 ohms. Why? Because when you have only 2 resistors in parallel, right, which are identical, okay, let me show you. This is not really theory, but you should understand this by now. If you have R here and R here, so identical resistors, the effective resistance of the parallel branch is going to be R over 2, or half R, right? And that's interestingly, very interesting that happens. But just go on with it. We're doing circuits already. Okay, I think I'll end this here and do it separately.